Okay. Now, the second thing that we have to be able to explain is what's known as emissions, emission spectra. Okay. When you add, this is almost like a cathode ray tube. When I add electricity to one of these tubes filled with a gas, I get a unique color. Okay, everybody's familiar with neon. Okay, in other words, this is kind of the idea behind neon lights. Neon is all red. Okay, so if it's neon, you see red lights. And so this discovery, well then how do we explain this? Because again, there's nothing about it. As soon as I show electricity, they glow like this. More importantly, when I take that glow, when I take that bit of light and I actually put it through a prism, okay, when we prism, we see a continuous, there's a continuous spectrum, there's a rainbow of colors. Instead, what we see with those individual spectra is we actually see what's known as a line spectrum, okay, individual notes of color. Okay, and I can only show you this example. I can show you part of the screen. So what you can see is we are looking at black lines. As soon as I shift to this side, I see what's known as emission spectra. Okay, and that's where you see just the lines of color. Notice how these lines of color correspond with where these black areas were in the complete spectra. This is what's known as absorption, which we're going to talk about next, and then this is the line emission. Notice it doesn't matter what element I click on, each element has a very unique spectra. You kind of get the idea. Now, the reason we care about this again is since this is unique, well, how do we explain it? How do we explain that every single element has a unique line spectrum? Well, that's what Bohr did. The biggest thing here is to recognize that we have energy. In other words, electrons maintain energy levels. And those energy levels are constant and there's no gap, there's no space in between. So one may be at an energy level of 1, the next one's at an energy level of 2, and there's no such thing as an energy level of 1/2. Okay? Second thing is to keep in mind that electrons that are in these permitted orbitals have certain energies, and increasing energy moves the electron further from the nucleus. Okay, so if we see increasing energy, that electron's moved further and further away from the nucleus. And the other thing that's real important here is energy can be absorbed or emitted by that electron. This ties back into what you talked about in biology with photosynthesis, in that the electrons became excited. Well, one of the things you want to recognize here is when we talk about it, here's my nucleus, okay, here's the electron's energy level. Okay, if that electron gets struck by light, okay, it jumps energy levels. Okay, and now it's suddenly out here at this energy level. It's moved further away. It's gained energy. Okay, but the problem is out here is very unstable. Okay, the electron does not want to stay out here. So what it does is it falls back down, does what's known as return to the ground state, and when it returns to the ground state, it emits a photon. It emits light, and it emits the same light that it absorbed here. So energy is completely conserved. Okay? Now, again, what that means is it has to absorb, so we have to see the absorption of light, and then that light is emitted. So we have what are known as absorption and emission lines. So far so good. Okay? Make sure there's a couple of links on the page to look at absorption and emission. Make sure you play with that a little bit. And now let's talk about the reason we care about this is flame tests. Okay, this is in essence going to be our next lab. So when we talk flame tests, how close to done? Okay, so now when we talk flame tests, what we're looking at is the flame test then is where we get to see the practicality of these emissions. In other words, we see very unique, we said, remember it's a color, so, it's a fingerprint, so we get to see the unique fingerprints of these different wavelengths, of these different... Alright, here we go.
In this experiment, we are going to look at the characteristic colors given to flames by alkali metal compounds. The first flame is the red flame caused by lithium. Lithium chloride on a platinum wire gives a red flame when inserted into a Bunsen burner flame. Next, sodium chloride. Sodium chloride is placed on the platinum wire. It gives a characteristic yellow color when placed in the Bunsen flame. These colors can be used to qualitatively identify the presence of the metals. A yellow flame always indicates the presence of sodium. Finally, potassium chloride. Potassium chloride on platinum wire is placed in the flame, and it gives the characteristic lilac color. All these colors arise because the alkali metal atoms are raised to excited states by the temperature of the flame, and then return to the ground state, emitting light of a characteristic frequency.
In other words, a characteristic color. Okay, and so that color is what again makes it unique. Okay, now when we look at this again, keep in mind what we're talking about. Here's my nucleus, here's my electrons. My electrons literally absorb energy. Okay, light comes in, it absorbs energy, it ends up out here. It can't stay out there, so it falls back down, and when it falls down, it emits light. And that emission is what we get to observe in terms of the flame tests. All right, so here are the practice problems. Remember to pause and then solve, and then play. Don't forget to pause. Okay, so that's basically the last one, so make sure if you have questions you bring those in tomorrow.